Alright, let's dive into the guts of your computer, specifically the Linux operating system. Now before your eyes glaze over, I promise we're not going to get bogged down in a bunch of technical mumbo-jumbo. Instead, let's talk about something we can all understand: a kitchen. Imagine you're running a restaurant. You have a big, ambitious goal to cook a magnificent multi-course feast. To do this, you need resources: a kitchen space, ovens, ingredients, cutting boards, and a recipe book. This entire setup, this self-contained culinary operation, is a lot like what we call a process in the world of computers. It's a single big job with everything it needs to get done, all neatly packaged together. But what if one person trying to cook an appetizer, a main course, and a dessert all at once is just too slow? The soup gets cold while the steak is searing, and the ice cream for dessert melts. It's chaos. You need a better way to work. You could build a whole new separate kitchen for each dish, but that would be incredibly expensive and wasteful. You'd need to buy new ovens, new refrigerators, and stock each kitchen with its own set of ingredients. That seems like overkill, doesn't it? This is where our story gets interesting, because there's a much smarter, more efficient way to handle this culinary challenge. This is where the idea of a thread comes into play. The lone chef in the kitchen. So, let's really build out this idea of a process. A process is like a lone chef who has been given their very own exclusive kitchen. In Linux, when you launch an application, say your web browser, a music player, or even a simple calculator, you're telling the operating system to set up a brand new isolated kitchen for that one specific job. This kitchen comes fully stocked. It gets its own set of tools, like memory space to work in, its own private pantry of ingredients, the data it's working on, and its own copy of the recipe book, which are the program's instructions. It's a completely self-contained world. The beauty of this setup is isolation. Our lone chef in one kitchen can't accidentally spill soup on the chef in the kitchen next door. If one chef makes a colossal mess and sets off the fire alarm, or in computer terms, if a program crashes, it doesn't bring down the entire restaurant. The other kitchens or other programs keep running completely unaffected. This is a huge deal for stability. It's why you can have a video game crash, but your music player keeps on playing your favorite tune without a hitch. Each process is protected from the others, living in its own little bubble, which is a myth we can definitely confirm as true and essential. Linux, acting as the restaurant owner, keeps a very close eye on each of these kitchens. It maintains a list of every single process currently running. It knows which kitchen belongs to the web browser chef and which one belongs to the spreadsheet chef. It decides whose turn it is to use the main power supply, the computer's processor or CPU. It's like the owner telling the chefs, "Okay, chef browser, you get to cook for a few milliseconds, now stop. Chef music, it's your turn." This happens so incredibly fast that it looks like all the chefs are cooking at once, a brilliant illusion of multitasking. But there's a cost to this isolation. Setting up a whole new kitchen every time you want to start a new task takes time and resources. You have to build the walls, install the oven, stock the pantry. It's a heavy-duty operation. In computer terms, creating a new process is expensive. It uses up a fair bit of memory and takes a noticeable amount of time for the operating system to get everything ready. Now let's bring in the crew. Threads are the answer to the inefficiency of building a whole new kitchen for every little task. Remember our team of chefs working together in one kitchen? That's exactly what threads are. A single process. Our one kitchen, the web browser for example, can create multiple threads to handle different jobs simultaneously. One thread might be responsible for loading the images on a web page. Another thread could be playing a video embedded on that same page, while a third thread is busy responding to your mouse clicks and scrolling. They are all part of the same web browser process. The key here is what they share. Unlike separate processes, which have their own private everything, threads within the same process share most of their resources. They work in the same kitchen or memory space, use the same set of ingredients, program data, and follow recipes from the same book, which is the application's code. This makes them incredibly lightweight and fast to create. Hiring a new chef to join the existing crew is way easier and cheaper than building a whole new restaurant from the ground up. This is why threads are often called lightweight processes. They're the nimble, specialized members of a larger team. This sharing, however, introduces a new kind of challenge. It's the flip side of the coin to the safety of processes. Since all the chefs' threads are in the same kitchen, they have to be careful not to get in each other's way. What if two chefs try to grab the last egg from the carton at the exact same time? Or what if one chef starts cleaning the cutting board while another is still using it to chop onions? That's a recipe for disaster. In the computer world, this is called a race condition. Programmers have to be very careful to coordinate the actions of their threads, using special tools to ensure they don't corrupt their shared data. So, threads are a trade-off. You gain incredible speed and efficiency because you're not duplicating resources. You can have many threads working in parallel on a single complex problem, which is fantastic for performance, especially on modern computers with multiple processor cores. But you trade the built-in safety of process isolation for this speed. A mistake in one thread can mess things up for all the other threads in that process. If one chef in our crew starts a fire, the whole kitchen might go up in flames, shutting down the entire operation. The application crashes. So how does Linux, our master head chef, decide what to do? It doesn't really. The application's programmer does. The programmer decides whether their task is better suited for multiple separate kitchens, processes, or a single kitchen with a skilled crew, threads. Linux just provides the tools and manages whatever the programmer asks for. Let's think about when you'd choose one over the other. You'd use processes when the tasks are largely unrelated, running a web browser, a word processor, and a music player at the same time. Those are perfect candidates for separate processes. They don't need to share data, and you absolutely want them isolated so a crash in one doesn't affect the others. On the other hand, you would choose to use threads when you have a single large task that can be broken down into smaller parallel subtasks. Think about a video editing program. One thread could be rendering the video frames, another could be processing the audio track, and a third could be updating the user interface to show you the preview. All these tasks need access to the same raw video and audio files. It would be incredibly inefficient to create separate processes, as you'd have to copy that massive video file into each process's private memory. Using threads is the only logical choice here. Let's recap this with a simple myth-busting summary. The myth might be that processes and threads are basically the same thing. Busted. The reality is they are fundamentally different tools for different jobs. Processes are like separate, independent kitchens. They are heavy, safe, and isolated from each other. Think of them as individual applications running on your computer. Threads are like a team of chefs working in the same kitchen. They are lightweight, fast, and share resources, but they must be carefully coordinated to avoid chaos. Think of them as the different things happening inside a single application. Ultimately, the power of a modern operating system like Linux comes from its ability to manage both of these models flawlessly. It can run hundreds of isolated processes to keep your system stable, and within each of those processes, it can manage thousands of threads to make your applications fast and responsive. It's a beautiful two-tiered system of organization. It's the difference between a single cook trying to do everything and a perfectly run restaurant with multiple kitchens and expert crews, all orchestrated by a master chef. And that, my friends, is a myth confirmed.